Okay, let's start the second lecture, which is on the applications of random walks on networks. So there is a various applications in the review paper, which this lecture is based on, covers much more applications than what is listed here. So actually, in this lectures I will cover actually 4 topics. I forgot one. So the one is page rank, community detection, response-driven sampling, and the voter model opinion formation dynamics. Actually, right? Okay, let's carry on. So if I am asked to raise the most important or perhaps famous application run walks and narrow side rates, and many people would probably agree on the page rank, which is the algorithms, very famous algorithm used for the Google search, proposed in say 1990, and this forms an basis of the Google search algorithm. So of course, Google was established by these two people, Brian Page and pretty rich, of course. And then page rank is not just an algorithm to rank websites, and because it is a network algorithm which ranks nodes in a single network, so it has various applications such as those listed here. I want to read them. Okay. And technically, so it is the stationary density of the discrete time run walk on network, which we learned in the first lecture. But why? What is justification? So, okay. So another thing is what's the relationship between the networks and this web search engine? So they started to say those people, event page, looked at this the whole web as a graph. So this is a website A, and this is a website B. And if there is a hyperlink, if you click on the hyperlink on page A, if you suppose that we can jump to page B. But page A has various hyperlinks in general, so clicking each of which carries you to a different website like this. And then let's say CD, whatever. And page B in turn has various, the potential various hyperlinks, which might carry you back to page A, or might carry you to page E, or different page F. So in this way, we can regard that the website, a set of websites, at least those which are connected to each other in the strong sense, actually. So they form a network, single network. So then our interest is to rank the different websites according to some criterion. And importantly, this is directed network because the hyperlink is directed. So even if there is a link from B to E, or say there's two E's, sorry, so F, but there may not be a edge, a link, hyperlink back from F to B. It might not exist. So this is essentially the directed network. And then if we think how to rank such websites when the key term is input, and then of course the search, say ranking should be restricted to the websites which are related to search keyword. But otherwise, these websites related to search keyword would form network if there is the hyperlink from A to B and so on, right? In this way. And if you think about how important a web page is, which is a page rank, which is what page rank does. So the rank should be large when these three criteria are satisfied, or some of them are satisfied. Okay, if the node page I, receives many edges, it means that it receives hyperlinks from many websites. Okay, this makes a website A, node I, okay, let me consistent, let's use terminology I and J here. So the page I important, okay, good, very intuitive. But if this is a sole criterion, it will be easy for me to cheat the system to get my, say, Naoki's website very famous. because this is the case. If this is the only criterion, then I would create many fake websites which send some direct links to my main website. In this way, we can arbitrarily increase the number of, say, edges incoming to this website, which is essentially, say, in degree, which is okay, or they say you are using, say, weighted version in this lecture, so it might be denoted like this. But anyways, this is number of edges or weighted number of edges incoming to node I. Okay, but we need something. So we think, if we consider that it is important to receive hyperlinks from important websites, this is the second criterion. So even if I make many fake websites, well, the right, so very cheap website, each of which sends links to my main website, but these websites, new websites which I created, are not famous. So even though there are many incoming edges, they won't count to the importance of this node I. Okay, this is the second criterion. What is important is to receive a hyperlink from an important website. If this particular website is important, then it is important. It makes this website I important. Okay, so let's go back to see this figure. So the size of the circle represents the page rank. So it's better to get more edges than few edges. But if you say receive the same number of edges, it's important to receive them from the important nodes websites, rather than we receive the same number or even more numbers of edges from unimportant edges. The third criteria does something different. So if we receive a web link from this famous website, which is the case for both of these cases, but this case, in the first case, this famous say website important node sends only one edge to this edge, this node, sorry. But this in the second case, so this is as important as this one, but it sends many edges, one of which node 2 received. So in this case, we value this case more. So because, I mean, if there are, say, many, say, hyperlinks on the, let's say, certain node j, okay, the user would be perhaps baffled which one to click. At least, I mean, each hyperlink carries less value if there are many hyperlinks. But let's say if this is a famous website and if this has only one hyperlink, you may probably be tempted to click this because it has only a single, say, hyperlink to some other website I. So this case is more important. So okay, so the one, so okay, the three criteria, they are adapted to define the centrality, importance of nodes, which are websites, are these three things. And actually, these things can be realized by this. This is a formula which we have seen already, right? So this is a this is a stationary density of random walk. So if as we suppose the random walk, which I mean let a walker travel from one node to another, and so forth. This is a stationary density, how often the walker visits each website. Okay, so if walker is a surfer, random web surfer, which is a human being, say, okay, so we just, the human, let's say, if I'm a surfer, then if I see many links, and idealized case, this is idealized case, right? So I would click one of the hyperlinks on the website, with the probability, say 1 over the number of, say, hyperlinks, okay? Then it carries myself to some different say page, let's say A. And if there are, say, 3 hyperlinks on page A, so I just click one of them with the probability 1/3 to go to, say, different page, which is, let's say, D, and so forth. So this, I mean, simple model, say this models, simple random walk models, the behavior in the web surfer if the surfer is random. Of course, the actual surfer is not random. But anyways, if we allow this interpretation, this is the stationary density. If there are many surfers, like myself, let's say, in a website, and then this is the fraction of, say, the random surfers visiting, say, each website. Okay. I'm saying that this, say the stationary density of the discrete time run walk fulfills these three criteria. So why is this the case? So let's have a look at this. Okay, I haven't have this slide, so let me explain using this slide. So let me just erase something. Sorry, so because I'm say scribbling too much bit. Okay, if you look at this, say one line, each equation of this. Okay, this is the equation which determines the stationary density at node R in terms of, say, the other stationary stationary density of, say, other nodes J. Okay, J of course sends a directed link to I. Okay, let's ask the first question. So does I receive many edges? If this happens, then is I regarded to be important? Seems to be so, because if I receives many links, or like this, okay, and then there are many terms, because this Aij is, let's say, if there is the link, say the network is unweighted, and it is equal to 1 only when there is an edge from J to R. Otherwise, this is the adjacency matrix which we learned in the first lecture, right? So it is equal to 0 if there is no edge. So the summation, number of, say, terms in the summation is essentially the number of, say, the edges which come into the node I. So if this is large, of course all things are positive, right, not negative, so it would increase the importance of node I. Okay, the first criterion. Okay, so second one, if I receive edges, here's a typo, sorry, but edges from important nodes, what happens? Important nodes means the large value of, say, pj. So if this value is large, of course it would contribute to the importance of the node I as well. So good. So what is this? I receive exclusive edges, valuable edges. So if j sends many edges, one of which I receive, then it's not good. If j sends, let's say, just one single edge, which is received by I, it is nice. So is this the case here? So let me just assess this equation again, right? So if, okay, this is the degree, right? So look at this carefully. So this is out degree. So it's j out, weighted out degree. So if j sends many edges like this situation, so in this number becomes large. So the denominator becomes large. So this fraction becomes small. So contribution of the term to pi becomes small. So it's no good. But if, let's say, if this out degree is small, then this denominator is small and this one becomes large. So the contribution of this pj to the increase in the pi would be large. So this third criterion is also satisfied. Okay, so here in this way, so random walk and the importance of nodes satisfying these three criteria are directly related. Okay, the mathematics. So the empirical networks are usually not strongly connected. What do I mean by this? Strongly connected means that we can go, okay, if you have the network, so we can go from anywhere, let's say I to j, along some paths. Even if I and j are not directly connected, if you go along through the direct edge, we can somehow reach j. So if this is the case for each pair of, say, nodes, we say that the network is strongly connected. But this is not the case usually, so for many reasons. So some of the nodes pages in the web just receive links and it doesn't send any edge. So we say that this is a sink. And also in the terminology of, say, the web graph or the page rank, they are called dangling nodes. So mathematically, the out degree or the weighted out degree, weighted nodes to outgoing weighted, out degree, yes, or the node strength is equal to 0. Okay, this is a very problematic in the sense that if the random walk reaches here, so we wonder where to go to. Or should it go back to the original place? Maybe. but the random walk is not defined if there is no outgoing edge, which is problematic. And this sink makes the network not strongly connected already, and there are many of them in the say this web graph. If this is a page containing just a photo, then of course photo doesn't usually have an a hyperlink, so it would be a sink. Source is a the node having in degree a weighted in degree equal to 0. There is no incoming edge. Okay. Is this realistic? It is actually. So if I create an very superficial website, then it wouldn't receive any link from elsewhere. So if this is the case, then this becomes 0 because fake website wouldn't receive a good hyperlink from anywhere. So, and also say there may be the case that say there are many multiple islands which are not really connected, or even if it is connected, unless there is a link back from this island to that island, if this doesn't exist, then this is not strongly connected, right? So this is related to transient nodes and components. So if I start a random walk from here in the absence of such a kind of edge, so let's say I call this island island 1 and this is island 2. If I start from island 2, okay, the random walker would travel in this island 2 sometimes, some steps, and then at some point of time, so it enters island 1. Okay, travel, but never we can say go from island 1 back to island 2. So in this sense, island 2 is transient, defined as transient states and transient component, right? So if such a transient nodes components exist, then say the network is not strongly connected. So in this case, so if we calculate the page rank or equivalently the stationary density, they all become 0. Because in the long run, every random walker is trapped in the island 1. So island 1 nodes have some positive the stationary density, but all these nodes in the second island has a 0. The stationary density 0 or say page rank. No good. But nevertheless, we want to say rank those nodes as well. So to avoid this, so we allow workers to teleport to other nodes with probability 1 minus 1. What does it mean by this? So with some probability, okay, so I don't use the fixture now. So we go to a randomly selected node without using network structure. Okay, so we have an underlying networks where we are working on, right? So we are random walkers, but with certain probability, we do not use the network structure and select the destination of the next hop with the probability UI. So with probability UI, okay, this is normalized properly. And we decide to go to a randomly selected node, which is UI, right? And otherwise, we do the usual random walk. In this way, so we can escape from, let's say, sinks. The sink, okay, this is a different question. Okay, so anyways, we do this. So if we do this, so even if this, let's say in the previous slide, I had 2 islands, right? Island 1 and 2. But even if we have reached island 1 and with some probability, okay, we do the random jump, and with certain probability we visit some nodes. So it may happen that they say we can have a chance to say go back to island 2. So in this way, this treatment makes the effective network. Effective means that we consider the effect of say this random jump, which is essentially a complete graph with some weights, right? So even if the original network is not strongly connected, this treatment makes the network strongly connected. Okay. A popular choice is to just uniformly choose the destination of the random jump when random walker does the random jump with probability 1 minus alpha. And also, so we have to say think about dangling node. So this is the dead end, right? So we probability 1 minus alpha, so it does the random jump, go elsewhere, that's fine. But what happens with this probability alpha? We have to use a normal the random walk, but there is nowhere from here to go to. So we define that in this case, at dangling nodes, we teleport, we do the random jump to with this probability, with probability 1. Okay, in this way, we can avoid the problem of the dead end. So then the random walk is well defined, and even if the network is not strongly connected, this new random walk effectively works on the strongly connected network, and this is a popular choice. Of course, there is no definite way to determine the value of alpha. If alpha is very large, then the effect of the original network becomes strong. If alpha is very small, let's say 0.1, okay, the usual random walk part is used with the only small probability, and in most of the times, then the walk will be randomly hopping, so the network effect is diluted. So the idea is that we want to rank nodes in the original network, so we want to make alpha large. But if the alpha is too large, then we rarely use these random jumps. So sometimes the convergence becomes small, slow, etc. So this is a compromise, I think. And the effective network is defined by this, okay? So this is the original networks, and this is the random jump dilution. But we can also define effective network and this transition matrix like this. And then the page rank is using this effective network transition probability matrix. And the page rank is its stationary density. Okay, this is some walk around of the random walk when we consider page rank. So here's an example, but this example is the same as before actually. So I raised this example in say lecture 1, and the important thing is as follows. Okay, so we found that okay, these two do not coincide each other, meaning that even if the say the in degree is large, okay, so these two have almost the same in degree, but this is larger. But if you look at the stationary density, this is larger, right? That's one thing. And if you look at the say compare 3 nodes with only one incoming node, then stationary density page rank is very different. What's happening? So that we can't say okay, this is one criterion, but it doesn't say explain everything. So let's look at these 3 nodes and look at which node these nodes receive a single link from. So the V2 receives link from V5, right? And 5 receives link from 6. And 7 receives the unique link from where? 5, right? Good. And 5 is not very important, right? So the 7 is receiving a single link from a not very important node, okay, which makes the rank or stationary density of this node relatively small. Okay, similar for this, because 5 is not important, but 5 receives a single link from node 6, sorry, which has a very high this is stationary density importance, which makes the rank of this node very large. Of course, this is still smaller than so many other nodes, but if you compare between the 3 in degree 1 nodes, this is very large, right? So more than 6 times larger stationary density. Okay, this effect is this. So and also, so we can perhaps I'm spending too much on time this. I don't do this, but I can find the actual case for this within this figure. Okay, applications. So as I said, so this is the particular application where the author used the page rank to rank tennis players. So the idea is to say draw an edge from the player to player. So in this way, so for example, the Federer collects many edges because it won. So I think this is winner, loser. This is the direction of the edge by convention. So in this way, so okay, so winner collects many edges if it wins. Let's say Federer collects many edges because he has won many other sort of famous players. But the important thing is that it is this the rank becomes larger if the node player beats other strong players, not just players but strong players, right? So this is one of the sense of the page rank. So this is a one application. So the author say Filippo Radicchi. So they use this algorithm to say rank players of tennis across time, so across period, and to talk about the historically strong players like this. Okay. So let me go to the next application, which is the community detection. So community net structure is one of the probably most the studied say topic in the say network science as a whole, and it's called graph partitioning, or the same as they say graph partitioning in other domains like computer science. And the idea is to say partition the nodes, let's say, into disjoint groups, such that there are many edges within the group, whereas there are relatively a small number of edges across different groups. And I am saying that the community detection is very much related to the random walks. So we have already seen this such an example by the argument of the Cheeger constant in the previous lecture, which I made. But we are going to talk about algorithms to detect community structure based on random walks. So okay, here's a very famous example of the karate club networks. Okay, I don't explain what this network is, but using either some algorithms or by predetermined labels, we can find communities. Okay, here, so the nodes are colored according to the one of the two communities each of the node belongs to. Okay. Why random walks? The idea is as follows. Why random walks are useful for finding communities? His idea is as follows. So if you run the random walker, if the network has a community structure, so it would wander within a community for a long time in a single community because there are many edges inside before transiting to another community. So because these across community edges are relatively rare, so it's rarely, or at least with less frequently used. So they wander in this community for some time, and then go to another community, and then the tendency is that the random walker would wander within the community for some time, and then go to another community. So this is the intuition. So the various algorithms have been developed based on this idea to find communities. I just named some of them. So the walk trap may not be necessarily the most famous, but it's easier to explain. So let me start from this. So let's consider the undirected and unweighted network for simplicity. And then the authors defined the distance between nodes in this way. So what this? Okay, we start random walker from I, and they ask the probability with which we reach node L after n steps. Okay, so we have this situation, right? So if we start from node, let's say 1, it means 1, 0, 0. So if we plot this, so we discover that this is a probability that the node L is reached after n steps, and the same probability, but when the starting node is changed to the J. So we are starting from two different nodes and asking the probability that it reaches at the same node. And if these two probabilities are similar, of course, it's this difference, or square of the difference is of course small. And we do this exercise for all nodes and sum the effect up. And the large degree, particularly in the undirected networks, would imply that they say we would have many random walkers. So we discount the effect by considering this is a degree, by the way, degree of node L, which I didn't read. Oops. Degree number of edges connected to node L. And we regard that this number is, if this number is small, then nodes I and J are similar in the random walk sense. In this case, the assumption is that, say, such a pair of nodes with small Rij distance, right, would belong to the same community. Okay, so one calculates this, Rij for each pair of nodes, which is not that difficult. And then once we have calculated the distance matrix, we run the hierarchical clustering. So with small figures, so we just enlarge this. So this is from Wikipedia, so there's nothing special here. And then this connects, there's some nodes into one cluster. So this is like a node 1, 2, etc. I don't know. If we kept but this the order can be swapped. And then this algorithm does to connect these nodes close to each other in terms of Rij. So in this way, so we create clusters. So if we say the number of clusters, let's say 4, then we cut it here. And those who belong to each branch defines a community. This is the idea. Good. And right. So the only problem which remains is how to choose n. Of course, another problem is how to choose the number of clusters, which is always difficult. But apart from that, so we have to determine n. If n is very large, then this becomes very difficult because regardless of the starting node I or j, so this probability approaches the stationary density at L. So if this is the case, then this quantity becomes 0 more or less, so all the distances become 0, so all the nodes are similar. So we have to ensure that n shouldn't be too large. Okay, second algorithm, which is well used by the community, particularly, is called the infomap. So what is this? So the idea is to use again. So the idea is intuition behind this algorithm is the same. So random walkers would stay in this community, single community, before transiting to another community. And this algorithm can assume, say, generally directed or weighted networks, and encode each node into binary code word. So this is the idea. So this is a coding-based algorithm. So let's say if node 1 is represented by a binary word 000, okay, that's one choice. And then the node 2 should be encoded to another word, right? So if this is the same, then we can distinguish between two. In this way, we can uniquely determine the codes. Then say if the walker moves in this direction, 3, 6, 3, 1, 8, let's say. So the sequence of, say, the trajectory of the walker is coded into this binary sequence. This is 3, right, V3. And okay, so if we cut each one, okay, say every 3 bits, then rediscover the trajectory. Okay, fine. And then, but we don't have to use the same length of binary string for each node. And unique decoding requires prefix free. So if this one is coded into 000 and 2 is coded in 0001, if this is the case, when we have seen the sequence 000, we can't say whether this is V1 or this is part of V2. So this is no good. So we have to avoid this. So this is the basics of the coding theory. And there are various ways to do this, but Huffman code, so-called the famous prefix-free so-called code, which yields short binary sequences. So the matter now is to say how to assign the code word for each node, 000 or 0100, whatever. So we have choices as long as the whole code system is prefix tree. So the idea here is that the frequency visit node should use a short word. So it appears many times, so this should use a short code word. And the channel entropy, which is defined by this, gives a lower bound of the mean code word length. But this also exposition doesn't talk anything about these random walks yet. So we do this in the next slide, I hope. So also let's use the coding scheme for local to the individual communities. This is the idea by the authors. Okay, so if we have 4 communities, okay, we use these codes when the walker entered and exited, and the same for the other 3 communities. And if you look at this figure, you notice that there are many same codes used in different communities. Let's say 10 is used here, 10 is used here. Is it okay? Or also, let's say 01 is used here and here, for example, or actually every community. So it contradicts the notion of the code in the sense that say each node should have a different code word, but it doesn't, because we are assuming now that the code word code book is local to each community, and we present the entry and say the exit of the walker from the community into and say out of the community using this particular signal. So in this way, if the walker starts from here, okay, let's say we put this in signature, and then we start from this node, and in the next step, the walker moves here, and then here, and then importantly, the walker leaves this community, so 00 is put, and the walker enters this right top community, so we have to put 00. And then say 10 is the first node to visit within the second community. And then in the next step, the walker moves here, 01, and then here. So this, trajectory shown in red is translated in this binary sequence. And the aim is to try to make this code length, mean code length short. So in this way, we want to discover the communities. Okay, this has an applet in the authors, say Martin Rosser's website, which is a fun thing to play, not just applet, but code and more information found in his website. And this is just a single application where the same authors tried to say find temporarily changing communities called mapping change. So this tracks how the different fields of research evolve across time. So the next topic is on respondent-driven sampling. So here the aim is to estimate the fraction of infected individuals, let's say, on a large network population, particularly a difficult to reach population where the respondents or the people don't really want to answer the questionnaires, where they are infected by HIV, for example. So how can we sample and estimate the population average of something like an age or whether these individuals are infected or not? So the respondent-driven sampling uses age tracing. So if I ask somebody and then they get answer, reply from him or her, and then I'll urge the respondent to rate some of his or her neighbors, and then ask those neighbors to ask the same question like an age. So here's an idea, right? To start from a single individual, and then after supposing that this person answers the question, then the respondent recruits neighbors to a survey by passing a coupon to each of them. And if they are successfully recruited, I mean those neighbors participate in the survey and then continue saying, and then calculate the weighted mean of the samples, for example, of the age, for example, to derive an estimate population of the population average of let's say an age. And important to the reward participants, particularly by the passing the coupons, other say people to successfully invite them to the say survey. Okay. So the are useful for discuss the difficult to reach populations because they are recruited by their friends. So it's relatively easy for them to participate. And it's a snowball sampling plus some mathematics. So here is just one example where the authors look at the HIV status, whether negative or positive, by using this technique, right? So because each sampling starts from a single seed node, and then this person would they recruit let's say 3 individuals and then so forth, right? So this idea is, yeah, okay. So why a weighted mean? So I said do we have to take a weighted mean, not just the mean. So the reason is this is so-called a friendship paradox. So you may have heard of this, but nevertheless, let me explain. So if you are here, and you suppose that you're a respondent, and then if you recruit somebody, let's say just one person, one of your friends, this friend, whoever he or she is, tends to have a large degree, right? So if you have, say, various friends having different degrees, number of friends, then if you choose a random edge to say which you have to reach somebody, then the tendency is that so if you pick somebody from the entire network, then it's really easier to reach this person having 6 degree 6 rather than this person having degree 2. And the probability that the U neighbor in a random network it's this person A is 3 times, meaning say 6/2 times larger than this person. So by reaching this person. So if you randomly sample by snowball sampling, then you're recruiting friends. This means that there is an intrinsic bias towards sampling large degree nodes, individuals. So we have to correct for this. For example, when we are estimating an age, we do not want to weigh too much the age of high degree nodes. We just want to have a size sample average. I mean population average, not sample. Sorry, so population average, right? So that's why we need to do some mathematics to correct for this. And here we use the stationary density of the random walk, which you are already seeing in this slide, I guess. Okay, let's say this y is a quantity which you want to estimate whose average, population average, on say, but this y is not for node I, like an infected or not by 1, 0, or age. And you assume that you sample NS individuals in sample set S. And we know by the first lecture that they say, assuming that they say the network is undirected for simplicity, the stationary density for the random walker to visit node I is proportional to the degree. Perhaps I should erase this to get it better. Okay, right. And then this N and this K, this is a population average, this is mean degree. It's to normalize this quantity. By normalization, I mean that this is a stationary density. So if you sum this quantity over all the nodes, it has to be 1 because this is a probability. So if you try to do this, we actually get this, right? And this is actually the case. Okay, so this is by definition n times its mean. Right? So it's 1. Good. So that's why we win this. But crucially, we don't know n. This is the number of individuals. We don't know this. We know the sample size, number of individuals in the sample, but we don't know the size of the whole population. And we do not know the mean degree of the network, because to know the mean degree, ideally we have to sample all the nodes, or we have to count all the number of edges in the entire network, which is something impossible. So we have to estimate them somehow. So this is a difficulty. This is a statistics problem, right? And estimator of this the population average of this quantity y is given by this. What am I doing here? Okay, so your sample size is ns. Of course, here you are summing up over all samples. So of course, you have to divide by ns. And this quantity is an estimate discount of yi depending on the say degree. So as I said before, so the large degree nodes are more often visited. So you have to correct for this, right? So this quantity on the denominator is a correction factor. So if the say stationary density is large, then you have to discount this sampling because this sample is more is often sampled than the population average. So this is a correct say normalized say correction factor because the mean of this is equal to 1. Right, that's obvious because mean or population here, let's say this is a population mean is equal to 1. Okay. So we know this. Well, we done this. So let's substitute this into this estimator. Then we get this, right? So we nicely can erase both n, which we don't know, and this estimator by this substitution. Okay, that's how we get this. So I have already explained why all these calculations are necessary because these quantities which are assumed to be obvious or at least can be easily calculated or even implicitly assumed in the theoretical calculation of various types of enumeration data analysis sometimes are not trivial. We cannot know this a priori, right? So that's how we have to do all those calculations. So here we say that it's not done yet because we don't know this quantity. We know Ki. If you sample the nodes, then we can ask him or her to say a number of friends we have. So this is something we can collect. And of course, you're asking, let's say, the age of say, each respondent. And we know the sample size, but you don't know this one. So you have to work a bit more to do this. Okay. To do this, we do the following. Okay, so we want to estimate this quantity. It's a mean of K, obvious, over samples. That's the best we can do. But as I said, so we have to discount this by this discounting factor to reduce the effect of the visiting hub very often as compared to low degree nodes. Okay, that's fine. And this is normalization for this. All right. And then if you substitute this. Not back, I mean substitute this into the denominator on both the numerator and denominator of the whole thing, and then we get this. Okay, so this is ki over the population, they say the network mean. So this ki and this cancels out, right? And even though this is something really difficult to obtain, but the same quantity appears on both, right? Now this should be this, right? So this quantity also cancels out on both sides. So that's how we get this. So this is a summation of 1 now, right? This quantity is 1. So this is sample size because there are ns terms. Okay, this is something we know. Good. So if you use this estimator to be substituted into this expression which we derived in the previous page, okay, we want to erase this quantity, right? And if you do this, we get this. Okay, so this is something we can get. Okay, you got samples and you got sample individuals degree and of course observable like an age. So and we calculate this. Okay, this is called this RDS2 estimator. Proposed in this paper, which is famous, I think. So as an application, if you want to know this proportion of nodes that have a discrete type LSL infected, then we should do this. So this is just an application of this one because now, so yi is a discrete binary variable such that it's equal to 1 if it is it's of type A, let's say infected. Otherwise, it's 0. So if we substitute this binary variable into this formula, okay, of course the denominator stays the same. And this one, okay, so take summation only when the say node is in S sample, of course, and also if it has type A. Okay, so then we get let's say estimated fraction of a individual's nodes having say particular type A like an infected. Okay. Thanks. So they will say almost 1 hour. So I prepared this slides for the water models, which are available the set of slides which I release online, but I skipped this one unfortunately. So here's the end. So let me just recap. So the materials here are essentially found in say our recent review paper, which is open access. And of course, we skipped various topics which are covered in the review paper, but not in the lecture. So those topics include them. Okay, these things. Okay, thanks for listening, and enjoy the rest of the lectures.